Welcome everyone. My name is Britt and I'm the marketing manager at Eatron Technologies. We're very excited that you're here for our next Talk to an Expert. We're going live every last Thursday of each calendar month, so keep your agendas open. If you're not following us yet on LinkedIn, please do so that you can keep in touch with all of our latest news and insights and next talks and events where we're attending. If you miss a Talk to an Expert, you can find us on YouTube and on Spotify and on our website. If you don't know us yet, Eatron is an international technology scale up dedicated to making software defined vehicles a reality for OEMs worldwide. Our house rules, if you have any questions, please put them in the chat at any point, and then our expert will answer them at the end. So today's expert is Ugur, our manager of AI and machine learning. Could you please tell us a bit more about yourself?
Sure. Hi, Brit, and hello, everybody, whoever is connected. I hope this is going to be a fruitful session for each of us. My name is Ugur Yavas. I have been in the automotive industry more than 10 years. Before Eatron, I was working in the AVL Turkey with the various roles, mostly focusing control software development and calibration. And in the last 4 years, I'm in Eatron, and I'm leading the artificial intelligence based projects and products, working closely with the battery management team in the last years, let's say. And my education background, I'm a controls grad from Istanbul Technical University, and same place I have the master's degree focused on model predictive control. And I'm about to finish my PhD soon, hopefully, focusing deep reinforcement learning. That's the short introduction.
Cool, thank you. So let's dive straight in. Let's talk first about the need for data. So could you tell me how important is data collection and the availability and quality for AI and ML solutions for BMS?
Sure. I think data is at the heart of any engineering problem that we are coupling with in today's high-tech industry, I would say. It's not just even AI, because we also see in any engineering software, the model-based solutions are getting more and more popular, and each model obviously needs parameterization. And I think with modeling, we can go for first principle physics based ones, or we can actually go sort of black box, so AI based solution. But then, yeah, obviously we need good quality of data. And if we narrow down the discussion, for example, in the AI side, I think in the last 5 years there's a growing trend, especially for the industrial solutions. It is not the most sophisticated neural network, or it's not the most complicated algorithm, but it's the cleanest data. It is the correct features. It is the right size of the data. It is the denoise data making the difference. And this is actually a big trend, data-centric AI, advocated by or casted by Andrew Ng, one of the pioneers in the field. And at Eatron, we really try to we follow this trend. We completely agree with it, and we really give a lot of importance, like how we collect the data, how we clean it later on, so on and so forth. And I think one interesting example, one of our products that we already applied for a patent, for example, and it could work for AI and non-AI solutions when you want to parameterize your equivalent circuit models. We have a deep reinforcement learning based design of experiment, let's say, designer, where it decides what to collect from the lab. And it is like an adaptive thing. The more information it gets, it reduces the number of total cycles you would run if you're doing it in a grid search, or if you want if you want to visit every single place that you want to model. But instead, with less lab time, it can bring you the information. So even with the data collection, there's a lot of room for improvement and innovation, I would say, and we're trying to keep it up with it.
Cool, thank you. Could you tell me a bit more about the selection of algorithm and features?
Sure. I think but yeah, let's say once we have the data, then the next is like, what are we solving, and actually with which features. So there are two aspects of it. Let's try to think about features first. In battery world, actually, we measure current, voltage, temperature from the cells, packs, modules, and then we may have access to the vehicle level information, and maybe if we are in cloud, we may have it, thousands of it in a central manner. And then obviously the question how we will use this data, like in the which scale and to solve which problem. I think what we are trying to do at Eatron, like for the variety of problems, we actually keep up or come up with a variety of solutions. For example, we could go for classification to find the cells that would have failure. We could go for regression task where we aim for getting the state of RUL, or we could actually go for time series forecasting. And depending on that, we could work with raw features running in 10 milliseconds range, or we could go for accumulated feature depending on the certain things during the life of the battery, for example, particular moment of a charging event or a discharging event. So all of this brings us like a selection of features using statistics and expert knowledge, and we have this pool, and later on we can actually do some sort of auto ML or ML ops to really iterate and get best out of the combination. So a lot of let's say development we have done in the maybe last year was all about automation and reduce the human touch as much as we can. So let's design the system at the beginning with our expert, but later try to come up with the best out of the data with the selection of algorithms. Then, yeah, that links us to the algorithms bit, where we again do not restrict ourselves with a single solution. And I think we try to be strong in both neural network worlds, where the AI is changing every day. So keep an eye on there, but also really use gradient boosted trees, for example, which is a strong solution in the tabular data, which is the problem most of the time for some of the battery AI problems, let's say. And there I guess like few more insights about maybe neural networks. Like we actually use neural architecture search, because again, as in this feature selection, designing a architecture by hand might not give you the best results, or might not, it could be a lot of time consuming. Like there are thousands of possibilities, especially with the advancement every day. There is a new neuron type like LSTMs, GRUs, transformers, attention layers, convolution layers, diluted convolutions. So instead, we really do it by the power of optimization and careful engineering.
Cool. Thank you. Could you elaborate maybe a bit on what Etron's AI slash ML features are for
Sure.
BMS?
Yeah, of course. So I think we can begin with let's say health related prognostic features. And I think the big catchword is always like remaining useful life, and it is valid for any device we use. We want to know when is our battery gonna die, in the next 100 days, in the next months, and then can we change it. And I guess the problem now, we can cast it in a different ways. Like the first thing is like I want to know when it will die, so this is like RUL estimation. Then I want to know how is my battery doing today, so this is state of health, and it can be actually solved both by AI or classical state estimation methods like Kalman filter. So we have both solutions available. Then there is the challenging bit. Perhaps it's not just now, I don't want a single number, I don't want to get it just my age, the predicted death age. I want to know how will I go there, the trajectory. Then this is called RUL or SOH trajectory, where we get the limited input, then try to forecast the future path of the battery. And I think this is one of the most critical things, and it could easily be leveraged by the connectivity and cloud. Because in batteries, there's a phenomena called path dependence. So each battery has a different story. Each battery in its own story while they're aging. So you have to know its past. You have to get a profile for it, and then you should also embrace the change, because if that profile changes, you cannot extrapolate. It will follow a new path. And the SOH trajectory or RUL trajectory is key to that, especially when it's connected to cloud. And one final thing, it is the anomaly detection. So we call it accelerated degradation.
Mm.
This time, we try to be unsupervised as much as we can. Let's say we have the fresh cells in our hands, and in a modern battery pack or module, there's lots of them, and we can measure their voltage, temperature, and current. Then the question is, can we identify the abnormal ones by just using that data? And yeah, that's the final, let's say, feature that we already have demonstrated good results in the laboratory partners.
Cool. Thanks. And then could you tell me about a bit more about the execution on the hardware, which I guess is the last step?
Yeah, definitely. And yeah, hardware is also, there are a lot of, let's say, different possibilities. And starting from, like, we could end up with a typical automotive ECU where you're restricted to run C code, or C code generated from MATLAB Simulink most likely. So let's say no Python, no Keras, no TensorFlow. So you have to be doing some transformation. And at the moment, we have established these conversions. We can port any algorithm to C, even if we develop them with Python and the classical deep learning frameworks or machine learning frameworks. And right after conversion to C, we can still call them from MATLAB Simulink. And then I think there is another challenge about the edge deployment. Let's say this hardware, let's assume it's the edge, so it's going to be in the electric vehicle or stationary device. What is the capability of the device? At the moment, we are in an interesting R&D project. We are trying to deploy our solutions to the ultra low consumption microcontrollers, neural accelerators, and then this requires a lot of experience and careful engineering about network compression, pruning, you know, sacrifice a little bit of performance, but still be able to run these tiny device with the desired frequency. So all of these are big challenges that we try to solve day by day.
Cool. Thank you. And then what is the importance and use of simulation for the solutions?
Simulation is playing a big part. Actually, starting from the maybe training, because the data is sort of sparse in the better world, especially if you're not sitting in the laboratory of a OEM. There is less data in the public database, so you may actually need to create your own data set by using your simulator and go with a synthetic data generation. I think one of the this was one of the biggest trends in the last 5 years in the self-driving cars, and I think we start to see the same trend in the better world, like in the last years. And the idea is really um, do maybe few cell tests still, but complement the remaining part, like go for a infinite amount of virtual data and train your solution. Then once you deploy it, you should start to fine tune your solution again. So it's also, I think, really important to kickstart your algorithm, uh, just reach a level that is acceptable to deploy. But
Mm.
then in the field, especially if it's connected, just keep collecting the field data and keep improving your solution. I think this is a very important pipeline and thing to be done. And another use of simulation, we put a lot of energy lately. um, we want to be able to again complement real world usage. So now we have a simulator in our hands, and we can really tell, let's say, let's create an electric vehicle taxi fleet in London,
Mm.
and let's observe what's going to happen in the next 5 years, how these each vehicle will age depending on the different use cases, temperature, driver profiles, traffic, so on and so forth. And then we can ask the same question, we can cast the same problem. Instead of London, let's go Dubai. And now we have the hotter temperature, different charging station availabilities, and our let's say synthetic data considers everything from the geography, from the climate, from the real world charging positions, the traffic information. And this obviously kickstarts a lot. Like before you really deploy something, you can have a initial feeling.
Cool, thank you. And lastly, on our very first Talk to an Expert, I spoke with Christoph about a little bit about advanced BMS and AI and stuff. So I was wondering if you could tell me a bit your opinion about AI for BMS and if we really need it. And yeah.
Sure, sure. I think this bit is kind of interesting because I'm in the sitting in the position as like let's say AI engineer or AI manager, whatever. But I actually like to see first, without AI, what are we doing? Because obviously there is a crazy big hype, and sometimes it's in winter, sometimes it's in summer for artificial intelligence. I think we have also seen in the talk of Kemal where he was talking like when you cast like AI, what is it? Like he says optimization, and obviously in some of the people they think Terminator, it will conquer the world, so on and so forth. But I think it's quite useful in the batteries due to few facts. First of all, there are a lot of things, reactions that are not completely solved by first principles. So
Mm,
you cannot really formulate, or maybe with at least in a couple of equations. At the moment, you have like maybe 10 to 20 different aging mechanism, partial differential equations, difficult to solve, slow to execute. And if you're lucky, if you really parameterize it well, if you spend a lot of enough time in the lab, then you may have this model for the aging. But then on the other hand, I do see a lot of benefit of going data driven, or at least combine the two solutions. So ultimately my expectation is like anything we go for, which requires a lot of data and continuous data streams, AI will have a word. And but it doesn't mean we will give it up to other algorithms. They can always work together in a hybrid manner. And that is, I think, something we are pushing heavily on Eatron, like these hybrid approaches.
mm. Okay, cool. Thank you. Well, thank you for answering all my questions. Let's look at what other people have put in the chat. I know a couple of Etronians have asked some questions to get people to, write their questions down. Very first one is Brian. He says, "Hey, Aura, great talk, super interesting topic. What kind of use cases for battery management systems do you expect in the midterm, especially when you consider industry trends like software defined vehicles and cloud connectivity?"
Well, I think I already touched a little bit about connectivity because connectivity really brings this continuous improvement, something we chase very strongly in Etron in every product we have. And in addition to that, I believe the strength of connectivity with thinking software defined vehicles, I always think more and more about individual experiences. So my car will understand me more. And when I
Mm,
say my car, it is also my battery. Like how do I drive the vehicle? What is my demand from my battery in which months? Like what is my daily use cases, my weekly use cases, and then all of these individual use cases should ultimately result a better parameterization of the complete algorithm to increase the efficiency. So what would it be for the user? Obviously, longer battery life, more range. And I think they're both possible. And I think we are really pushing and let's say do some research about gamification and driver warnings. Like, okay, I observed you for the last month
mm,
and you did this and that. If you
mm.
don't do them, your battery will last 2 months more. So this is sort of driver education or gamification, and I think we'll see a lot of applications like this in the future.
Cool, thank you. Hyri is saying, "Hi everyone, very nice to hear Ur. My question is, what is the role of AI in the mobility solutions with battery swapping? Thank you."
I think this is very interesting question, and again quite relevant with the connectivity because battery swapping is happening anywhere around us now with these micro mobility solutions, or some of the OEMs, I think like Neo. Instead of spend time with charging, you just get a new battery and leave the old one for charging. So there's a immediate changes in the battery you use, and then that brings us back to the path dependence. So I think anybody doing a battery swapping business should need cloud and connectivity and RUL AI models, or any remaining useful predictive model to check what is going on. So you have to really track the use case of those batteries to make sure how will they comply with their warranty, because you might end up with a guy who is almost using it very harshly versus
Mm.
someone using very lightly. You still own the charging control in your hands, but you should also monitor that beat. So it's, I think, like um, they call it in the industry battery certificate, or it's like, I think, your kind of resume, battery resume,
Mhm.
like what you have been doing. And this is crucial for battery swapping.
Cool, thank you. Hope that answers your question. Alexander is saying, what are the main applications of deep reinforcement learning for battery management systems?
Well, I think uh, this is a very interesting question. Deep reinforcement learning, the algorithm that beat the Go experts. So it is very big in the robotics, and I think it has also some place in battery world as well. So it is also sort of my PhD thesis and my personal interest. So I keep looking at it when I have free time, let's say, where it's being used. At Eatron, we use it for two things. One is to design, let's say, these data collection strategies in the lab.
Mm.
So that is already in a good maturity. We've seen the clear results because, yeah, you can cast that problem like giving the data collection points, which of the combinations would maximize my reward, and my reward is obviously having a better fit. So this can be casted as a reinforcement learning problem. And the second thing we are investing lately or investigating lately is about smart charging. If you
Mm.
have, let's say, a good digital twin, like let's say a sophisticated battery model, uh, which can tell you about the anode and cathode potentials when you apply different charging profiles, then this again becomes like a decision making problem where deep RL excels. So it can really tell you what should be the trade off, because you
Mm.
want to do it fast. You don't want the user to wait, but still you don't want to harm your battery or make it age faster. So this kind of problems with trade-off, if you cast the reward function in the right way and if you have the simulator to solve it, they are the great use case for the deep reinforcement learning.
Cool, thank you. I hope that answers your question. Um, Mukai, I'm not sure if I'm saying your name correctly. I'm really sorry. He's saying, hi, thanks for this great webinar. I'm really interested in battery management systems. How do you process data? Does it increase power consumptions due to ML or DL
Hmm.
algorithms?
Hmm. So I think this question could have multiple answers. Let's uh, try to answer as much as I can. But if there are follow-up, please find me in LinkedIn, Mujahid. I think the processing bit happens in the edge. So we have time series data available from voltage, current, and temperature. So if there is a solution that works directly with these raw inputs, then I should maybe create a window and feed it to my ML or DL. So I think the processing bit in this case is not much a worry, a concern. It's just a window of these three channels for the duration you want to feed in your, let's say, time series forecaster, could be an LSTM. And in the other way around, we have also different use cases. For example, in the edge CPU, again, we just process the features. This time from these three distinct measurements, we create 6 to 8 features. Those features are like statistics based. You can think like having the sum, having the moving average, or collecting few of them and fitting some curves to derive some information. But all of these actually are easy calculations. The difficult bit is running the deep learning one. If you end up with a large CNN architecture, I think which you shouldn't, then it is a problem. It is high consumption. But then the trend or the research we are seeing, the neural accelerators is taking place. So if you have a neural accelerator, then running the deep net is also not a problem. I hope
Cool.
this answers.
I hope so too. Burak is saying, with the problems you have mentioned, do you think that the AI based solutions will surpass the classical methods within the next 5 years?
Um, I think yes, I really believe in this, and I also see sort of a wake up or dawn of, let's say, rise of AI in the batteries. There are many interesting survey papers written by, let's say, big professors from the universities that contribute this field in the last 20 years, and I think there is a community getting larger and larger around, for example, open source data, open source competitions, and open source frameworks. Actually, for example, PyBAM is a great advancement where you have these sophisticated models, all open source. You can see the contributions. You can actually be part of it. And I think with this kind of community having more and more people, soon we should see like AI taking a big part in the BMS.
Thank you. Eden is saying, hello everyone, thank you for an interesting webinar. I have a question regarding the battery state of charge estimation using ML algorithms. Do you think there is space for ML algorithms in battery state of charge estimation, and how would you approach the potential problem of underfitting slash overfitting there?
Yeah, this is, I think, a challenging question, and yeah, this is something we are working on it first of all, and so I think, yeah, there is definitely room for it. But then here, I think the bar is too high because, again, like we are trying to design the best state of charge estimation with the typical, let's say, Kalman filter based approaches, and there the error is only just 1%. So it's a very good solution is there. But I guess here I would open the hybrid card instead of just going solely on a neural network, replacing that Kalman filter. That seems tricky, especially again, underfit, overfit. You would really survive with that based on your data. But I think the problem is when you expose your electric vehicle to the real world, there's infinite different use cases, and you cannot really think about it in the very first stage. And that's the power of adaptive things like Kalman filter. Depending on the measurements, it will keep adapting. So I guess what I think is more on the equivalent circuit model, which is the part of Kalman filter. There, I believe we could end up with a better neural cell model. Then it could maybe work with Kalman filter, so an hybrid solution.
I hope that answers this question. Mohammed saying, hello, Dr. Yavas and Britt. Thanks for this great talk. My question is, for safety critical applications, do you think explainable machine learning algorithms, mostly traditional ones, for example, random forest, may be a feasible solutions, or are they outdated? Of they are outdated, sorry.
Uh, I think explainable bit is obviously very important, and I think in case of safety critical or safety criticalness, I wouldn't be worry as much as I would worry for self-driving cars. I think you have to be, very precise there about the uncertainty quantification and other things because you would really cause fatalities. In BMS, it is really application specific. For example, if I'm predicting the age of my battery or when it will die, it is not critical as the other example I just give. But then if I'm actually try to detect thermal runaway, once again, we may end up with a fatality. So then I should really make sure my predictions, biased towards actually false positive instead of false negative, because one false negative means, you could end up with a fatality again, like a fire on the car, so and so forth. And I think random forest or tree-based approaches are anyway there, but the main problem is they are not expressive enough when you increase the dimension and amount of data. And I guess there again, this is also partly the problem of deep learning world. There is a growing research field in the maybe last 5 to 10 years about Bayesian nets, or combining these things together to get the sense of uncertainty, even not the explainability. If you still say like you're uncertain about your result, that's a little explanation.
Thank you. Our very last question of the day, Devin. Hello, you said that you would need good data for battery ML application. What would you consider as good data?
Yeah, I think this is a very nice question. So, I mean, good data is sort of a maybe wrong phrase. And yeah, thanks for giving me this chance to explain it a little bit more. So, a good data means, the data without noise or the noise that you can able to measure. The data doesn't have outliers, and the data really expresses, the experiment you go for. So, if we give few examples about, let's say, the things we face daily or real world, in an aging test, you came up with a actually, let's say, a test program. You say, I have 50 cells, and every day I will charge them with this profile, and I will discharge them with this profile. And then, some of the days something happens, electricity went down, some of your tests are interrupted, and then, for example, now you have to start, making decisions, or some of your sensors did not work, some of your sensors work, but it actually has the frozen measurements. With all of these, you have to come up with decisions. So this is the cleaning bit. I think good data is the clean data, could be the short answer. So you have to really make sure all the sensors are working in the plausible range with the desired experimentation.
Cool. Thank you. Well, we've gone through all the questions. If anyone would like to ask another question, just put them in the comments, and then or we'll answer them. We'll just answer your comment. So thank you so much for today and for the talk and to answer everybody's questions. It was a pleasure to have you on. Um,
Yeah, it was also my pleasure. Thanks a lot for this opportunity.
Thank you. And thank you for everyone for attending, and hope to see you in the next one. Bye.
Cheers. Bye.